Hello, and welcome to Space for Sleep. Imagine the solar system with almost everything removed. Remove the diagrams, the names, the neat colored circles, and the familiar order learned in childhood. Remove the idea that the planets are arranged close together like objects on a tabletop. Remove the bright illustrations that enlarge every world until it seems easy to reach. What remains is a star surrounded by an extraordinary amount of darkness. Near the center, several small planets move through the star's light. Farther out, giant worlds follow slower paths. Beyond them lie icy bodies, scattered orbits, a vast magnetic bubble, and perhaps trillions of dormant comets so distant that the sun appears as little more than a bright star. The solar system is not simply a row of 8 planets. It is a structure extending from the furnace of the solar core to regions where the sun's gravity competes with passing stars and the tides of the Milky Way. It contains worlds with metal cliffs, sulfuric clouds, oceans, volcanoes, rings, buried seas, nitrogen glaciers, magnetic storms, and landscapes that have not been touched by sunlight in billions of years. It also contains nearly all human history within one tiny part of one tiny orbit. Every city, language, ocean voyage, argument, discovery, and quiet night has occurred on one planet moving around one star. Every spacecraft ever built remains within the gravitational domain of that star. Even the Voyagers, now traveling through interstellar plasma, have crossed only the boundary of the solar wind. They have not crossed the full reach of the solar system. Tonight, we will travel outward slowly. There is no need to rush. The distances are too great for ordinary speed to have much meaning. Instead, we can move at the pace of attention, allowing each region to become clear before it fades behind us. We will begin with the Sun, which contains almost all the mass and supplies almost all the light. Then we will pass through the rocky worlds, the belt of asteroids, the giant planets and their moons, the realm of Pluto, and the thin frontier where the solar wind ends. Beyond that frontier, the Sun will continue to hold distant objects with gravity long after its atmosphere has given way to the surrounding galaxy. The tour is quiet because most of the solar system is quiet. Sound cannot travel through the vacuum between worlds. Collisions occur, storms rage, magnetic fields snap and reconnect, and eruptions throw material into space. Yet no sound crosses the emptiness to announce them. From far enough away, even the most violent event becomes light and motion without noise. The solar system formed about 4.6 billion years ago from part of a cold interstellar cloud. The cloud contained mostly hydrogen and helium, along with dust enriched by earlier generations of stars. Those earlier stars had manufactured carbon, oxygen, silicon, iron, and many other elements, then returned them to space through winds and explosions. The atoms in Earth, in the planets, and in living bodies therefore have histories older than the sun. Something disturbed one region of the cloud. It may have been a shock wave from a nearby massive star, the pressure of surrounding star formation, gravitational turbulence within the cloud, or some combination. The exact trigger is not known. Gravity began drawing material inward. As the region collapsed, it rotated faster. This is the same basic effect seen when a spinning skater draws in their arms, though the forming solar system was not a solid object. It was a cloud of gas and dust whose particles collided, exchanged momentum, and gradually flattened into a disk. Most of the mass gathered at the center. Pressure and temperature increased until a protostar formed. Around it stretched a rotating protoplanetary disk, broad, turbulent, and filled with grains no larger than smoke particles. Those grains began to stick. Electrostatic forces joined tiny particles. Collisions produced larger aggregates. Some collisions broke objects apart, while others allowed them to grow. Millimeter grains became pebbles. Pebbles collected into larger concentrations. Gravity became increasingly important as planetesimals formed. The growth was not smooth. The young disk contained pressure waves, vortices, changing temperatures, and material drifting inward toward the sun. Objects collided at different speeds and angles. Some grew into planetary embryos. Others shattered and were recycled. Near the young sun, it was too warm for water, methane, and many other volatile compounds to remain frozen. Rocky and metallic materials dominated. Farther out, beyond changing frost lines, ices survived. Solid water and other frozen compounds greatly increased the amount of material available for building planetary cores. This temperature difference helped produce two broad families of planets. The inner worlds became relatively small and rich in rock and metal. The outer planets developed massive cores capable of gathering hydrogen and helium, or accumulated large amounts of water, ammonia, methane, and other materials that planetary scientists traditionally call ices, even when those substances now exist as hot compressed fluids. The planets did not necessarily form exactly where they orbit today. Young planetary systems are dynamic. Giant planets exchange angular momentum with disks and with smaller bodies. Their orbits can migrate inward or outward. Resonances sweep through populations of planetesimals. Entire regions can be emptied, mixed, or repopulate. Models of the early solar system suggest that Jupiter and Saturn strongly influenced one another and the smaller outer worlds. Uranus and Neptune may have formed closer to the Sun before moving outward. Countless icy bodies were scattered toward the Kuiper Belt, the Oort Cloud, the inner solar system, or interstellar space. The modern arrangement is therefore not a preserved diagram of formation. It is the result of formation followed by billions of years of migration, collision, resonance, erosion, heating, cooling, and loss. The earliest surviving solids found in meteorites formed about 4.567 billion years ago. These calcium-aluminium-rich inclusions provide one of the most precise starting markers for solar system history. Within a few million years, larger bodies were already heating internally. Short-lived radioactive isotopes released energy. Metal melted and sank. Rock rose. Some early asteroids differentiated into cores, mantles, and crusts, becoming small worlds before later collisions broke them apart. Planetary embryos struck one another. The impact that formed the Moon was part of this violent age, though its exact details remain under study. Mercury may have lost part of its original exterior through impacts, evaporation, or unusual formation conditions. Uranus may have acquired its extreme tilt through one or more collisions, although alternative histories are possible. The neat planets we see now emerged from disorder. A scale model helps reveal how much emptiness surrounds them. If the Sun were reduced to the size of a grapefruit, Earth would be roughly the size of a grain of sand more than 10 meters away. Jupiter would lie much farther down the path. Neptune would be hundreds of meters from the small grapefruit sundae. The nearest star would not be placed at the end of the room, the street, or even the city block. On the same scale, it would be thousands of kilometers away. This is why the planets almost never align in the compact way shown in illustrations. Their orbits occupy enormous circles at different speeds. Their diameters are tiny compared with their separations. Spacecraft spend most of their missions crossing darkness rather than passing close to visible worlds. Light itself requires time. It takes a little more than 8 minutes to travel from the Sun to Earth. It takes tens of minutes to reach Jupiter, more than an hour to reach Saturn, and several hours to reach Neptune. A radio command sent to a distant spacecraft is never a live conversation. By the time a reply returns, the spacecraft has continued moving, the planet has rotated, and events have already become history. Distance turns every exploration mission into a form of planned patience. The Sun's gravity does not end at the last planet. Gravity weakens with distance, but never switches off. The planets orbit because they are falling continuously through curved paths around the Sun. Dwarf planets, comets, dust, and spacecraft follow the same law. Far away, other influences become comparable. Passing stars tug at distant comets. The gravitational field of the Milky Way produces a gentle tide. At some point, an object can be more easily removed from the Sun than retained. There is no single sharp edge that satisfies every definition. The heliopause marks the end of the solar wind's dominant bubble. The outer Oort cloud marks a much larger gravitational frontier. The region where stable solar orbits give way to the galaxy is broader and less visible than either. A tour from the Sun to the edge therefore crosses several kinds of boundary. It begins inside a star. At the very center of the Sun, gravity compresses plasma to a density many times that of water and a temperature near 15 million Kelvin. Hydrogen nuclei move fast enough to overcome part of their electrical repulsion. Through a sequence dominated by the proton-proton chain, hydrogen is transformed into helium. A small amount of mass becomes energy. Every second, the Sun fuses hundreds of millions of tons of hydrogen. Several million tons of mass are converted into energy during that process, emerging eventually as radiation, particle motion, and neutrinos. The neutrinos escape almost immediately. They interact so weakly with matter that most pass through the Sun, Earth, and human bodies without leaving any trace. Detectors deep underground capture a tiny fraction and confirm reactions occurring in a core no camera can see. The energy carried by photons has a slower journey. Inside the radiative zone, a photon does not travel in a straight line to the surface. It is absorbed, re-emitted, scattered, and transformed countless times. The energy may take tens of thousands or hundreds of thousands of years to move outward through the dense interior. Farther from the center, convection becomes efficient. Hot plasma rises, cools, and sinks in broad circulating motions. At the visible surface, the photosphere, the tops of convective cells create a granular pattern. Each granule is comparable in scale to a large terrestrial region, yet the full Sun contains millions of them. The photosphere has a temperature near 5,800 Kelvin. It is not a solid surface. It is the layer from which visible light can finally escape freely enough to reach space. Above it lies the chromosphere and then the corona, an extended atmosphere heated to more than 1,000,000 Kelvin. The corona is much hotter than the visible surface, an apparent reversal that remains an active subject of research. Magnetic waves, turbulence, and countless small reconnection events probably transfer energy into the thin outer atmosphere. The Sun is not a quiet sphere. It rotates differentially. The equatorial regions turn faster than the polar regions. Plasma motion stretches and twists magnetic fields. Over an approximately 11-year cycle, the global magnetic pattern evolves, sunspot numbers rise and fall, and the Sun's magnetic poles reverse. Sunspots appear dark only because they are cooler than their surroundings. They mark regions of concentrated magnetic field where convection is partly suppressed. Around them, magnetic loops can store enormous energy. When magnetic fields reconnect, the Sun can produce flares and coronal mass ejections. A flare releases radiation. A coronal mass ejection throws billions of tons of magnetized plasma into space. If that material reaches Earth with the right orientation, it can disturb the magnetosphere, brighten auroras, alter radio communication, increase radiation exposure, and induce currents in electrical systems. Space weather begins at the Sun. The solar wind is a continuous outward flow of charged particles embedded in magnetic fields. It does not move uniformly. Fast streams emerge from coronal holes. Slower wind has more complex origins. Eruptions overtake ordinary wind, and create shocks. Together, these flows inflate the heliosphere. The planets orbit inside the Sun's extended magnetic and particle environment. Their magnetospheres and atmospheres respond differently depending on distance, composition, and internal fields. Mercury has a small magnetic field but almost no atmosphere. Venus has a thick atmosphere but no global internally generated magnetic field. Earth has both a substantial atmosphere and an active magnetic dynamo. Mars has only patches of ancient crustal magnetism and a thin atmosphere. The solar wind therefore interacts with each world in a different way. The Sun contains about 99.8% of the solar system's mass. Jupiter contains most of what remains. All the other planets, moons, asteroids, comets, rings, dust, and spacecraft together contribute only a small fraction. Yet mass is not distributed in the same way as angular momentum. The Sun rotates slowly compared with the rapid spin one might expect from a collapsed cloud. The planets, especially the giants, carry much of the system's orbital angular momentum. Magnetic interaction between the young Sun and its disk help transfer rotation outward during formation. The Sun is middle-aged, but not unchanging. Its luminosity has gradually increased since the solar system formed. The young Sun was significantly fainter, creating a puzzle because geological evidence shows liquid water existed on early Earth and probably early Mars. Greenhouse gases, atmospheric pressure, cloud behavior, ocean circulation, and other factors helped compensate, though the full faint young Sun problem remains rich and complex. In the future, the Sun will continue brightening. Long before it becomes a red giant, increased solar energy will alter Earth's climate and eventually make surface oceans unstable. The timing depends on climate feedbacks and cannot be reduced to one exact date, but the long-term direction is clear. In roughly 5 billion years, hydrogen fusion in the core will end. The core will contract and heat while outer layers expand. The Sun will become a red giant, transforming the inner solar system. Mercury and Venus are expected to be engulfed. Earth's survival as a physical planet is uncertain, but its surface will already have been rendered unrecognizable. Later, the Sun will shed its outer layers and leave a white dwarf. The planets that remain will orbit a smaller, dim stellar remnant. Passing stars and long-term gravitational interactions may eventually rearrange or remove them. The solar system is stable on human timescales and temporary on cosmic ones. For now, however, the Sun remains in its long main sequence balance. Gravity pulls inward. Thermal pressure pushes outward. Fusion replenishes the energy escaping into space. The balance has lasted for billions of years, allowing planets to cool, atmospheres to evolve, oceans to persist, and life on one small world to become aware of the star that sustains it. From the Sun's visible surface, the first planet lies tens of millions of kilometers away. It moves quickly through intense light, completing an orbit before Earth has traveled even 1/4 of its own. We now leave the star and follow the solar wind inward toward Mercury. Mercury is the smallest of the 8 planets and the nearest to the Sun. Its average distance is about 58 million kilometers, though its orbit is noticeably eccentric. At its closest approach to the Sun, Mercury receives more than twice as much solar energy per square meter as it does at its farthest point. A year lasts only 88 Earth days. Its day is stranger. Mercury rotates 3 times for every 2 orbits around the Sun. This 3-to-2 spin orbit resonance means one solar day, measured from one sunrise to the next, lasts about 176 Earth days. The relationship creates unusual skies. From some locations, the Sun would rise, slow, appear to reverse briefly, and then continue. The effect occurs because Mercury's orbital motion changes rapidly near perihelion and can temporarily overtake the apparent motion caused by rotation. The planet's surface resembles the Moon at first glance. It is heavily cratered, gray-brown, and ancient. Large impact basins overlap older scars. Smooth volcanic plains fill low regions. Long cliffs cross the landscape. But Mercury is not simply a larger version of the Moon. Its interior is dominated by an enormous metallic core. By radius, the core occupies most of the planet. Mercury's average density is high, second among the planets only to Earth's when gravitational compression is included, and unusually high for such a small world. Why Mercury contains so much metal remains unsettled. A giant early impact may have removed part of a once thicker rocky mantle. Extreme heating near the young sun may have altered the material from which Mercury formed. Repeated erosive collisions may have stripped its exterior. It is also possible that metal-rich material was concentrated locally in the protoplanetary disk before the planet assembled. No single explanation has been confirmed. The metal core still produces a global magnetic field. The field is weak compared with Earth's and offset from the planet's center, but its existence was a surprise when Mariner 10 detected it in the 1970s. A world this small might have cooled and solidified internally long ago. Instead, at least part of the core remains fluid enough to sustain a dynamo. Mercury has almost no atmosphere in the ordinary sense. It possesses an exosphere, an extremely thin population of atoms knocked from the surface by sunlight, solar wind, and micrometeorite impacts. Sodium, potassium, oxygen, hydrogen, helium, and calcium have been detected. These atoms do not collide often enough to behave like weather. They follow ballistic paths, escape to space, or return to the ground. Mercury's environment is therefore a continuous exchange among rock, sunlight, particles, and vacuum. The surface temperature changes enormously. Near the equator at local noon, it can rise above 400 degrees Celsius. Before dawn, it can fall below minus 170 degrees. Mercury has one of the largest day-to-night temperature ranges of any planetary surface because there is no substantial atmosphere to carry heat from one region to another. Yet ice survives there. Mercury's axis is almost upright. Near the poles, the floors of some deep craters never receive direct sunlight. Radar observations from Earth first suggested bright deposits within these permanent shadows. NASA's Messenger spacecraft later provided strong evidence that many contain water ice, sometimes covered by a thin layer of dark organic-rich material. The contrast is remarkable. On the planet closest to the Sun, water can remain frozen for immense periods because local geography prevents sunlight from reaching it. Mercury is also shrinking. As the core cools, the planet contracts. The crust responds by breaking and thrusting one block over another. The resulting lobate scarps can extend for hundreds of kilometers and rise several kilometers high. Messenger found small scarps that appear geologically young, suggesting contraction may have continued much more recently than once assumed. Mercury also experienced widespread volcanism. Smooth plains and volcanic vents show that lava resurfaced large regions. Some vents are surrounded by bright deposits produced by explosive eruptions, indicating that volatile substances once existed within the interior despite Mercury's proximity to the Sun. Only 2 missions have explored Mercury closely so far. Mariner 10 flew past 3 times in 1974 and 1975, imaging less than half the surface. Messenger became the first spacecraft to orbit Mercury in 2011 and spent 4 years mapping the planet before ending in a controlled impact. A 3rd mission is now approaching. Bepi-Colombo, a joint project of the European Space Agency and the Japan Aerospace Exploration Agency, traveled through the inner solar system using gravity assists and solar electric propulsion. Its two orbiters are scheduled to enter Mercury orbit on November 21st, 2026, followed by deployment and commissioning before routine science begins in 2027. One orbiter will focus on the planet's surface, composition, gravity, and interior. The other will study the magnetosphere and the solar wind. Mercury remains difficult to reach because traveling inward is not simply falling toward the Sun. A spacecraft leaving Earth already shares Earth's orbital speed. To enter orbit around Mercury, it must lose enormous orbital energy without plunging into the Sun or passing the planet too quickly. The difficulty explains why the innermost planet has received fewer missions than Mars, Jupiter, or Saturn. From Mercury, the Sun would appear more than twice as wide as it does from Earth and several times brighter. The sky would remain black because the exosphere is too thin to scatter daylight. The ground would be illuminated with harsh contrast. Shadows would be nearly absolute except where light reflected from the terrain. At the poles, a person could move from brilliant sunlight into a crater where the ground has not seen the sun for billions of years. We move outward again. The sun shrinks slightly in the sky, but the next planet is wrapped in an atmosphere so dense that its surface is hidden from ordinary view. Venus is almost the same size as Earth. Its diameter is only slightly smaller. Its gravity is close to Earth's. Its bulk composition is probably broadly similar, with a rocky mantle and metallic core. For this reason, Venus was once called Earth's twin. The phrase now feels unsettling. At the surface, the temperature is about 465 degrees Celsius, hot enough to melt lead. Atmospheric pressure is about 90 times that at Earth's sea level. The air consists mostly of carbon dioxide, with clouds of sulfuric acid floating high above. The surface is hotter than Mercury's average daylight terrain despite Venus being farther from the Sun. The reason is not simply closeness to the star. It is the greenhouse effect. Sunlight passes through the upper atmosphere and heats the lower atmosphere and surface. Carbon dioxide absorbs outgoing infrared radiation. Heat is repeatedly exchanged and trapped within the dense atmosphere until the surface settles at an extreme temperature. Earth also depends on a natural greenhouse effect. Without it, our planet would be frozen on average. Venus demonstrates how profoundly atmospheric mass and composition can alter surface conditions. The phrase runaway greenhouse is often used for Venus, but reconstructing the precise sequence remains difficult. The planet may once have contained much more water and perhaps surface oceans. Climate models produce a range of possible histories depending on early rotation, cloud cover, topography, volcanic outgassing, and the brightness of the young sun. Some scenarios allow temperate surface conditions for long intervals. Others suggest Venus became hot early. The available evidence does not yet establish that Venus definitely possessed Earth-like oceans. What is clear is that most of its original water is gone. Ultraviolet light can break water vapor apart in the upper atmosphere. Light hydrogen escapes more easily to space, while oxygen reacts with the surface or is removed through other processes. The relatively high abundance of deuterium compared with ordinary hydrogen suggests substantial water loss over time. Venus rotates very slowly and in the opposite direction from most planets. One sidereal rotation takes about 243 Earth days. Its year lasts about 225 Earth days. A solar day, from noon to noon, lasts about 117 Earth days because the retrograde rotation and orbital motion combine. The cause of this state is uncertain. Large impacts may have altered the spin. Atmospheric tides may have influenced it. The planet's rotation could have evolved through a combination of solar gravity, internal friction, and atmospheric motion. The atmosphere rotates much faster than the solid world. High cloud layers circle the planet in only a few Earth days. Winds exceed several hundred kilometers per hour at altitude, even though the surface, turns almost imperceptibly beneath them. Near the ground, winds are much slower, but the dense air gives them substantial force. A gentle breeze in such a thick atmosphere can move dust and exert pressure unlike a similar wind on Earth. Venus has no liquid water ocean and no plate tectonics operating in the familiar terrestrial style. Its surface, however, is geologically complex. Vast volcanic plains cover much of the planet. Mountain belts rise above them. Circular coronae mark regions where hot mantle material may have pushed upward and deformed the crust. Long fractures, lava channels, and volcanic domes appear in radar maps. The planet may still be volcanically active. Comparisons of radar images from the Magellan mission have identified a vent that changed shape over several months in 1991, consistent with volcanic activity. Other observations suggest recent lava flows and changing atmospheric gases, though confirming present activity requires new measurements. Venus may lose heat through episodes rather than continuous plate recycling. Its crust could remain relatively immobile for long periods while heat accumulates below, followed by widespread resurfacing or regional volcanic events. Models range from stagnant lid behavior to more mobile and episodic forms of tectonics. The age of the visible surface is also uncertain. There are far fewer impact craters than on Mercury or the Moon, showing that much of the surface has been renewed. Craters are distributed broadly rather than concentrated only in old terrains, which once led to the idea of a near-global resurfacing event. More recent interpretations allow a complex history of overlapping regional processes. The clouds make direct imaging difficult. Visible light cannot penetrate to the ground, but radar can. NASA's Magellan spacecraft mapped nearly the entire planet in the early 1990s by sending radio waves through the atmosphere. Several Soviet Venera landers survived on the surface long enough to transmit images and measurements. Their views showed flat slabs of volcanic rock beneath an orange sky. The longest-lived surface craft operated for a little more than 2 hours before heat and pressure destroyed it. No lander has worked there since the 1980s. That long gap is expected to end with a new generation of missions. NASA's Da Vinci mission is designed to send a probe through the atmosphere, measuring noble gases, chemistry, clouds, and the lower atmosphere while imaging the mountainous Alpha Regio region during descent. NASA's Veritas mission is planned to map the surface from orbit with high-resolution radar and study the planet's gravity and composition. Its launch is planned no earlier than 2031. The European Space Agency's Envision mission will also study Venus with radar and spectroscopy, linking surface features with internal and atmospheric processes. Together, these missions aim to answer questions that reach beyond one planet. Why did Earth and Venus diverge so dramatically? How long can a rocky planet retain oceans near the inner edge of a habitable zone? Does a planet need plate tectonics to regulate climate over billions of years? How often do Venus-like worlds occur around other stars? Venus is not merely a warning or a failed Earth. It is a complete planetary outcome, shaped by its own atmosphere, geology, rotation, and history. At cloud-top altitudes, pressure and temperature become surprisingly Earth-like. This has inspired proposals for balloons and aerial platforms that could survive far longer than landers. The clouds remain acidic and chemically harsh, but flight is easier in dense air than on Mars. Suggestions of life in the Venusian clouds have received attention, especially after disputed reports of phosphine. Follow-up studies have produced conflicting results and alternative explanations. No convincing evidence of life has been established. The question remains open in principle and difficult in practice. A droplet in the clouds would face extreme acidity, limited water activity, ultraviolet radiation, and changing altitude. Any biological claim would require multiple independent lines of evidence. From above the cloud deck, Venus can appear calm and almost featureless. Below, it is a world of pressure, heat, moving air, and volcanic terrain. We continue outward toward the third orbit. Here, the surface is neither hidden by a global cloud layer nor exposed directly to vacuum. Blue oceans reflect light. White clouds move. Brown and green land masses break the water. A large moon circles nearby. Earth is familiar, but familiarity can conceal how unusual its combination of features is. It has stable surface oceans, an atmosphere rich in nitrogen and oxygen, active plate tectonics, a long-lived magnetic field, and a biosphere that alters the air, rocks, oceans, and climate. None of these features can be understood alone. Liquid water depends on pressure and temperature. Climate depends on sunlight, greenhouse gases, clouds, ice, oceans, land, and life. Plate tectonics exchanges carbon among the atmosphere, oceans, crust, and mantle. Biology changes weathering and atmospheric composition. The magnetic field interacts with the solar wind, while the atmosphere itself provides most of the direct shielding at the surface. Earth is not simply at the right distance. The habitable zone defines a broad range where surface liquid water might be possible under suitable atmospheric conditions. It does not guarantee habitability, and planets outside it can contain subsurface oceans. Earth's long-term habitability emerged from a history rather than one perfect location. The young planet was struck repeatedly. Its interior differentiated. A global magma ocean may have cooled. Water arrived from material incorporated during formation and from later impacts. The atmosphere evolved through volcanic outgassing, escape, chemical reactions, impacts, and biology. The first life appeared at least several billion years ago, though its exact origin and timing remain uncertain. For most of Earth's history, life was microbial. Oxygen began accumulating significantly only after photosynthetic organisms transformed the environment. Complex multicellular life appeared much later. The modern atmosphere is therefore not merely a starting condition for life. It is partly a product of life. Earth's magnetic field is generated by motion in the liquid outer core. Convection and planetary rotation organize electrical currents within molten iron alloy. The resulting field forms a magnetosphere that redirects much of the solar wind. The field changes over time. Its poles wander and reverse. Its strength varies. During reversals, the planet does not lose all protection, and geological records show life has survived many such events. The atmosphere remains the main shield against ultraviolet radiation, cosmic particles, and meteoroids at the surface. Plate tectonics continually renews Earth's crust. Oceanic plates form at mid-ocean ridges, move, cool, and return into the mantle at subduction zones. Continents collide and separate. Mountains rise and erode. Volcanism releases gases. Weathering removes carbon dioxide and carries dissolved material to oceans. The carbon cycle acts as a long-term climate regulator, though not a perfect thermostat. Earth has experienced global glaciations, warm greenhouse intervals, mass extinctions, enormous volcanic provinces, and rapid climate shifts. Habitability does not mean stability without change. It means that life has persisted through change. The moon is central to Earth's story but should be described carefully. It is unusually large relative to its planet, yet the term double planet has no official universal definition and is not commonly used as a formal classification for Earth and Moon. The Moon formed very early, probably from debris produced by one or more giant impacts involving the young Earth and another planetary body. The traditional single-impact model remains influential, but details of mixing, impact geometry, and lunar composition continue to be refined. The Moon's gravity raises tides in Earth's oceans and solid body. Tidal friction transfers angular momentum from Earth's rotation to the Moon's orbit. Earth's day lengthens gradually, while the moon recedes at an average present rate of about 3.8 centimeters per year. That rate has not been constant through history because oceans, continents, and tidal resonance have changed. The moon also influences Earth's axial motion. Its presence reduces some large variations in obliquity that might otherwise occur, but the popular statement that it simply stabilizes Earth's climate enough for complex life is too strong. Climate depends on many factors, and a moonless Earth could still have had a complex history. The lunar surface preserves events erased on Earth. Ancient craters record impacts. Dark Maria are basaltic plains formed by volcanic eruptions billions of years ago. Bright highlands contain old anorthositic crust. Permanently shadowed polar regions preserve water ice and other volatiles. Human exploration is returning there. Robotic missions from several nations are studying the poles, surface chemistry, and interior. The moon is both a scientific archive and a practical destination, close enough for repeated missions, yet difficult enough to test technologies needed farther away. From the moon, Earth appears 4 times wider in the sky than the moon appears from Earth. It hangs nearly fixed above the near side because the moon is tidally locked. Clouds change. Continents rotate into view. City lights appear faintly on the night side. From Earth, the rest of the solar system has always been observed through the filter of our own atmosphere and perspective. From the moon, our planet becomes one world among worlds. We leave the Earth-Moon system and continue toward Mars. Mars is the outermost of the 4 terrestrial planets. Its orbit lies about 1.5 times farther from the Sun than Earth's, and a Martian year lasts 687 Earth days. The planet is about half Earth's diameter and has a little more than 1/10 Earth's mass. Surface gravity is 38% of Earth's. Mars looks red because iron-bearing minerals in its dust have oxidized. The color is not uniform. Dark volcanic sands, pale sediments, bright polar frost, exposed rock, and seasonal dust create a planet of subtle browns, ochres, grays, and blacks. Its atmosphere is thin and dominated by carbon dioxide. Surface pressure averages less than 1% of Earth's sea level pressure, though it varies strongly with elevation and season. Carbon dioxide freezes onto the winter pole and returns to the atmosphere in spring, causing the total atmospheric mass to rise and fall. The thin air cannot retain heat efficiently. A warm afternoon near the equator may approach temperatures comfortable by terrestrial standards, while the same location becomes bitterly cold at night. Polar winters fall far below the freezing point of carbon dioxide. Mars has weather. Clouds of water ice drift above mountains. Carbon dioxide ice clouds form at high altitude. Dust devils cross plains. Local storms grow, merge, and sometimes surround the entire planet in suspended dust. The sky is often butterscotch or pink because fine dust scatters sunlight. Near sunrise and sunset, the region around the sun can appear blue. This reversal of familiar colors arises from the sizes and optical properties of Martian dust particles. Mars also has seasons because its axis is tilted by about 25 degrees, close to Earth's tilt. The seasons are unequal in length because the orbit is more eccentric. Southern summer occurs near perihelion and is shorter and warmer than northern summer. This asymmetry influences winds, dust storms, and polar caps. Modern Mars is cold and dry at the surface, but its ancient landscapes record flowing water. Valley networks cut through old highlands. Delta deposits spread into former lakes. Rounded pebbles show transport in streams. Minerals formed through interaction with water occur across many regions. Some channels were carved by catastrophic floods. Others resemble branching river systems sustained over longer intervals. Sedimentary layers preserve repeated wet and dry conditions. Early Mars was not necessarily a permanently warm ocean world. The young sun was faint, and climate models struggle to maintain above freezing temperatures globally for long periods with carbon dioxide alone. Warm episodes may have been regional or intermittent, driven by impacts, volcanism, orbital cycles, greenhouse gases, or clouds. Yet liquid water clearly existed often enough to leave extensive geological evidence. Mars lost much of its atmosphere over time. Its small size allowed the interior to cool. The global magnetic dynamo ended early, leaving patches of magnetized crust but no strong planet-wide field. Solar radiation and the solar wind then interacted more directly with the upper atmosphere. NASA's MAVEN mission has measured ongoing atmospheric escape and helped reconstruct how water and gas were lost. Not all water escaped. Large amounts remained frozen in polar caps and beneath the surface. Radar and neutron measurements reveal ground ice at high latitudes and in some mid-latitude regions. Glacial forms preserve buried ice under protective debris. Brines may form temporarily under certain conditions, but stable liquid water is difficult at the present surface because pressure is low and temperatures are cold. Reports of possible subglacial lakes beneath the South Polar Cap remain disputed. Radar reflections can be interpreted in several ways, including unusual ice or mineral layers. Mars is a world where uncertainty often lies only a few meters beneath the ground. Its geography is immense. Olympus Mons rises more than 20 kilometers above the surrounding plains and spreads across an area comparable to a large country. It became so broad because low gravity allowed a huge volcano and because the crust remained relatively stationary over a long-lived source of magma. On Earth, plate motion carries crust away from hotspots and produces chains such as Hawaii. On Mars, repeated eruptions could pile lava in one region. Nearby, the Tharsis Rise holds other enormous volcanoes and a vast bulge in the crust. Its formation altered the planet's stresses, drainage, and perhaps even its orientation. Valles Marineris extends for roughly 4,000 kilometers. It is not simply a canyon cut by one river. It is a system of fractures, collapsed terrain, landslides, layered deposits, and channels, probably linked to the growth of Tharsis and later erosion. At its deepest, the chasm walls descend several kilometers. The northern hemisphere is generally lower and smoother than the southern highlands. This hemispheric difference may reflect an enormous ancient impact, internal processes, or several mechanisms acting together. Much of the north may once have held an ocean, but proposed shorelines and climate evidence remain debated. Mars has two tiny moons, Phobos and Deimos. They are dark, irregular, and may be captured asteroids or remnants of material produced by a giant impact. Their exact origin is unresolved. Phobos orbits so close that it circles Mars faster than the planet rotates. It rises in the west and sets in the east several times each Martian day. Tidal forces are drawing it inward. In tens of millions of years, it may break apart into a ring or strike Mars. Deimos moves outward slowly and appears more distant and calm. Mars has attracted more spacecraft than any planet beyond Earth. Orbiters have mapped minerals, ice, gravity, weather, and topography. Landers have measured the atmosphere and interior. Rovers have crossed ancient lake beds, volcanic plains, and sedimentary landscapes. Curiosity landed in Gale Crater in 2012 and continues examining an ancient environment where lakes and groundwater once existed. It has climbed the lower slopes of Mount Sharp, reading layers that record changing climate. Perseverance landed in Jezero Crater in 2021. Jezero once held a lake and river delta. The rover has studied igneous and sedimentary rocks, searched for environments capable of preserving biosignatures, and sealed selected samples in tubes. The small helicopter Ingenuity demonstrated powered flight on another planet. It was designed for a few experimental flights and completed 72 before a hard landing damaged its rotor blades in 2024. Its success changed expectations for aerial exploration of Mars and other worlds. The cache samples collected by Perseverance are among the most carefully selected extraterrestrial materials ever prepared for possible return. However, returning them is not currently a simple scheduled mission with a guaranteed date. NASA and the European Space Agency continue studying architectures for Mars sample return. The campaign remains a mission concept shaped by cost, technical risk, and program decisions. Statements promising that the samples will arrive during the 2030s are no longer secure. The samples may eventually allow laboratories on Earth to search for microscopic structures, organic chemistry, isotopic patterns, and environmental histories with instruments too large and complex to send to Mars. Even then, evidence of ancient life would require caution. Non-biological chemistry can imitate aspects of biology. Contamination must be controlled. Context matters. Several independent signals would be needed before a claim of Martian life could become persuasive. No confirmed life has been found on Mars. Methane detections have also produced a complicated story. Curiosity has measured seasonal and episodic methane at the surface, while orbiters have often failed to detect comparable amounts globally. Methane can be produced by life, but also by geological reactions and release from stored reservoirs. The discrepancy may involve local sources, rapid destruction, measurement limits, or processes not yet understood. Mars invites human imagination because it is both alien and accessible. A day lasts 24 hours and 39 minutes. The axial tilt creates seasons. The surface is solid. Water ice is available. These similarities make it seem almost familiar. The differences remain severe. Radiation at the surface is much stronger than on Earth. The atmosphere cannot be breathed and provides little pressure. Dust is pervasive and chemically reactive. Temperatures are low. Human habitats would require shielding, closed life support systems, reliable energy, and protection from isolation and reduced gravity. Mars is not a second Earth waiting unchanged for settlement. It is a planet with its own scientific value, history, and possible record of past habitability. As we leave Mars, the next region is often drawn as a broad ring of rocks. The asteroid belt begins gradually rather than at one sharp line. It occupies the space mainly between Mars and Jupiter, with most objects orbiting roughly between 2 and 3.5 astronomical units from the Sun. Science fiction often presents the belt as a crowded field requiring constant maneuvers. In reality, asteroids are separated by enormous distances. A spacecraft can cross the belt without seeing any asteroid unless its course is deliberately aimed toward one. The total mass of the main belt is small. Combined, all its objects contain only a few % of the Moon's mass. Ceres alone holds a large fraction, while Vesta, Pallas, and Hygeia account for much of the remainder. The belt is not the remains of a planet that exploded. There was probably never enough concentrated mass there to build an Earth-sized world. Jupiter's gravity stirred the region, resonances increased collision speeds, and migration in the early solar system depleted much of the original material. Planet formation began there, but growth was interrupted and reversed. The surviving bodies are not all unchanged primordial stones. Some are fragments of larger differentiated objects. Some were heated by radioactive decay. Some experienced volcanism, water rock chemistry, or core formation. Collisions mixed pieces from different depths. Meteorites arriving on Earth reveal this variety. Iron meteorites may come from the cores of shattered planetesimals. Stony iron meteorites may sample boundaries between metal and rock. Basaltic meteorites preserve volcanic crust. Carbonaceous chondrites contain primitive minerals, water-bearing clays, and organic compounds. A meteorite is not simply an asteroid fragment with one history. It can record the interstellar cloud, the protoplanetary disk, apparent body, impacts, exposure to cosmic rays, atmospheric entry, and time on Earth's surface. Ceres is the largest body in the asteroid belt and the only dwarf planet in the inner solar system. It is about 940 kilometers wide. NASA's Dawn spacecraft found a dark world rich in hydrated minerals, salts, ice, and evidence of past, or perhaps geologically recent briny activity. Bright deposits in a crater contain sodium carbonate and other salts. They appear to have formed when brines reached the surface and water sublimated away. Some deposits are surprisingly young in geological terms, suggesting Ceres retained internal liquid or slushy reservoirs long after formation. Ceres may be an ocean world in a broad sense, though any present liquid would be local and deeply buried rather than a global open sea. Vesta is smaller but more heavily differentiated. It has a basaltic crust, mantle, and metallic core. A giant impact near its south pole excavated an enormous basin and launched fragments into space. Some reached Earth as a distinctive family of meteorites. Dawn orbited both Vesta and Ceres, allowing direct comparison between two neighboring bodies with very different histories. Asteroid families trace collisions. When one parent body breaks apart, fragments begin with related orbits and compositions. Over time, sunlight, thermal forces, planetary encounters, and further collisions spread them. The Yarkovsky effect can slowly alter an asteroid's orbit because its warm surface re-radiates sunlight unevenly. For small bodies over millions of years, this tiny push matters. Resonances with Jupiter and other planets create gaps and transport routes. The Kirkwood gaps are regions where orbital periods form simple ratios with Jupiter's. Repeated gravitational nudges destabilize objects there. Some asteroids are pushed onto paths crossing Mars or Earth. Near-Earth asteroids are defined by their orbits, not their composition or place of birth. Many originated in the main belt and migrated through resonances. Most pose no threat. A small fraction pass close enough to require careful tracking. Planetary defense surveys measure their positions, sizes, and future trajectories. NASA's DART mission deliberately struck the small moon Dimorphos in 2022. The impact changed Dimorphos's orbit around the larger asteroid Didymos, demonstrating that a kinetic impactor can alter the motion of a small body. The test did not involve an asteroid threatening Earth. It was a controlled experiment in a binary system where the orbital change could be measured accurately. Europe's Hera mission is traveling to the system to examine the crater, mass, internal structure, and full effects of the impact. Planetary defense is not the destruction of asteroids. It is the early discovery of hazards, precise prediction, and, if needed, a small change applied many years before a possible collision. Time is the most valuable tool. Asteroids also preserve chemistry relevant to life's origins. Japan's Hayabusa 2 mission returned samples from Ryugu in 2020. NASA's OSIRIS-REx mission delivered material from Bennu in 2023. The samples were collected directly and protected from uncontrolled exposure, giving laboratories context that ordinary meteorites cannot provide as reliably. Bennu's material contains water-altered minerals, carbon, nitrogen, ammonia, amino acids, all 5 nucleobases used by DNA and RNA, and a vast diversity of organic compounds. Later analyses also identified sugars including ribose and glucose. These discoveries do not mean Bennu contained life. The compounds can form through non-biological chemistry. Their importance lies in showing that early solar system bodies carried a rich inventory of ingredients that could have been delivered to young planets. Bennu's parent body once contained liquid water that altered minerals and organics before later collisions assembled the rubble pile visited by OSIRIS-REx. Ryugu also records water-rock interaction and organic chemistry, while differences between the two samples show that primitive bodies did not all evolve identically. The asteroid Psyche offers another kind of history. It is a large main belt object rich in metal, though it is not simply an exposed pure planetary core. NASA's Psyche spacecraft used a Mars gravity assist in May 2026 and is expected to reach the asteroid in 2029. The mission will investigate whether Psyche is part of a differentiated body's interior, a metal-rich primitive body, or something more complicated. Farther ahead, NASA's Lucy spacecraft is exploring Jupiter's Trojan asteroids. These bodies share Jupiter's orbit around the Sun, clustered near stable gravitational regions ahead of and behind the planet. They may preserve material from different parts of the early outer solar system, mixed during giant planet migration. Asteroids are small, but their stories are not. They record failed planets, broken planets, wet parent bodies, metallic interiors, organic chemistry, orbital migration, and ongoing hazards. The belt marks a transition. Beyond it, the planets become enormous and their systems of moons begin to resemble miniature solar systems. Ahead lies Jupiter, bright enough to cast a faint shadow under dark terrestrial skies and massive enough to have shaped the architecture of everything we have passed. Jupiter is the largest planet in the solar system. Its mass is more than twice that of all the other planets combined. Its diameter is about 11 times Earth's, and more than 1,000 Earths could fit inside its volume. Yet Jupiter is not a solid sphere with a surface beneath its clouds. It is a deep atmosphere transitioning gradually into compressed fluid. Pressure rises downward. Hydrogen becomes liquid and then, at greater depth, enters a metallic state in which electrons move freely. A compact rocky or icy core may exist, but Juno measurements suggest the central region may be diffuse, mixed into surrounding material rather than separated by a sharp boundary. Jupiter probably formed early. Its growing gravity captured hydrogen and helium before the young sun's disk dispersed. Because it became massive so quickly, it influenced the movement of material across the entire system. The planet's orbit lies a little more than 5 times farther from the Sun than Earth's. A Jovian year lasts almost 12 Earth years. A day lasts less than 10 hours, making Jupiter the fastest rotating planet. The rapid spin flattens the planet at the poles and drives powerful atmospheric dynamics. Cloud bands stretch around the world. Light zones and dark belts move at different speeds. Jet streams flow east and west. Storms form where currents interact. Ammonia ice, ammonium hydrosulfide, water clouds, and deeper chemistry contribute to the colors and layers. The Great Red Spot is the most famous storm. It has persisted for at least the era of modern telescopic observation, though its size, color, and shape have changed. It is currently smaller than in the 19th century, but still broad enough to compare with Earth. The storm rotates as a vast anticyclone. Below the visible clouds, Juno has found atmospheric structures extending surprisingly deep. The familiar bands are not merely a thin painted surface. They connect to winds reaching thousands of kilometers into the planet. Near the poles, Jupiter looks different. Juno revealed clusters of cyclones arranged around central polar storms. The north and south have distinct patterns, maintained in a delicate balance by rotating fluid dynamics. Jupiter radiates more energy than it receives from the Sun. The excess comes from slow contraction and internal heat left from formation. As the planet cools, gravity compresses it and releases energy. This internal warmth helps power weather even at great distance from the Sun. Jupiter's magnetic field is the strongest planetary field in the solar system. Electrical currents in metallic hydrogen generate a vast magnetosphere. It extends millions of kilometers and forms a long tail away from the Sun. Charged particles become trapped and accelerated to dangerous energies. For spacecraft, Jupiter's radiation belts are among the harshest environments in planetary exploration. Electronics require shielding, and trajectories must limit exposure. The magnetosphere is not controlled by the solar wind alone. Io supplies enormous amounts of material. Volcanic gases escape from the Moon, become ionized, and form a torus of plasma around Jupiter. The planet's rapid magnetic rotation sweeps this plasma through the system. Auroras glow near the poles. Some are driven by the solar wind, while others are linked magnetically to Io, Europa, and Ganymede. These moons leave footprints in Jupiter's upper atmosphere, creating currents across hundreds of thousands of kilometers. Jupiter has more than 100 confirmed moons, ranging from the 4 large Galilean worlds to small distant objects on tilted and retrograde orbits. The irregular moons probably include captured bodies and fragments of collisions. Their clustered orbital families preserve episodes of capture and breakup. The 4 Galilean moons were discovered in 1610. Watching them change position around Jupiter helped show that not everything orbited Earth. Io is the innermost of the 4. Its surface is covered in sulfur compounds, lava fields, mountains, and volcanic deposits. Tidal flexing caused by Jupiter's gravity and orbital interactions with Europa and Ganymede continually heats the interior. The result is the most volcanically active world known. Some plumes rise hundreds of kilometers. Lava eruptions reshape the surface so rapidly that impact craters are difficult to preserve. Io demonstrates that a small moon can remain geologically extreme when orbital energy is converted into heat. Europa lies beyond Io. Its bright, icy surface is crossed by dark lines, ridges, disrupted blocks, and regions where the crust appears to have broken and shifted. Multiple lines of evidence indicate a global saltwater ocean beneath the ice. The ocean may contain more liquid water than all Earth's oceans combined. Tidal heating helps prevent it from freezing completely, though the thickness of the ice and the structure of the seafloor remain uncertain. Europa is scientifically important because water, chemical ingredients, and energy may coexist. This does not mean life has been found. It means the moon may contain habitable environments. NASA's Europa Clipper launched in October 2024 and is traveling toward Jupiter. It is expected to arrive in April 2030 and orbit Jupiter while making 49 close flybys of Europa. The mission will investigate the ice shell, ocean, composition, geology, and surrounding space environment. It is not a life detection mission. Its central question is whether places within Europa could support life. The spacecraft avoids orbiting Europa directly because repeated passage through Jupiter's strongest radiation would shorten its life. Instead, it spends much of each orbit farther away and dives close for concentrated observations. Ganymede is the largest moon in the solar system. It is wider than Mercury, though much less massive. Its surface combines old dark cratered terrain with younger grooved regions. Ganymede probably contains a deep ocean, perhaps layered between different phases of high-pressure ice. It is the only moon known to generate its own intrinsic magnetic field, likely from motion in a liquid metallic core. This creates a small magnetosphere embedded within Jupiter's much larger one. Callisto is the outermost Galilean moon. Its surface is ancient and densely cratered. The enormous Valhalla impact structure spreads across the landscape in concentric rings. Callisto is less strongly heated by tides than the inner moons, but magnetic measurements support the possibility of a conducting layer consistent with a salty subsurface ocean. Its old surface preserves a different chapter of Jovian history. The European Space Agency's JUICE spacecraft is also traveling toward Jupiter. It is expected to arrive in July 2031, study Jupiter and the icy moons, and enter orbit around Ganymede in late 2034. Europa Clipper and JUICE will complement one another. One focuses closely on Europa. The other compares Ganymede, Callisto, and Europa while studying Jupiter's wider environment. The Juno mission has transformed knowledge of the giant planet since entering orbit in 2016 and remains scientifically active into 2026. It mapped gravity and magnetic fields, probed atmospheric depths, observed polar cyclones, measured water, and made close flybys of Ganymede, Europa, Io, and small inner moons. On May 1st, 2026, it passed within about 5,000 kilometers of Thebe and captured the small moon from close range. Juno's long investigation has created a data archive that will be analyzed for years. Jupiter is sometimes called a shield that protects Earth. The reality is more complicated. Its gravity can eject comets and asteroids from the solar system, reducing some hazards. It can also redirect objects inward, create resonances, and deliver impactors toward the terrestrial planets. Jupiter is not simply a vacuum cleaner. It is an architect and disturber. During formation, its migration may have limited the mass available to Mars, reshaped the asteroid belt, and scattered icy bodies. The precise history remains model-dependent, but no account of the inner solar system can ignore Jupiter. The planet also hosts a faint ring system. Its rings are made largely from dust released when micrometeoroids strike small inner moons. They are far less massive and bright than Saturn's rings. From close range, Jupiter would dominate the sky with moving cloud bands and flashes of lightning. There would be no place to stand. A probe descending into the atmosphere would encounter increasing pressure, temperature, and wind. Radio contact would eventually fail. Deeper still, familiar distinctions between gas and liquid would disappear. We move outward across a broad interval of darkness. Saturn comes into view with a system so visually elegant that the planet itself is often treated as background to the rings. Saturn is the second largest planet. Its diameter is about 9.5 times Earth's. Its mass is much smaller than Jupiter's, making Saturn the least dense planet overall. The familiar statement that Saturn would float in water is a playful comparison of average density, not a physically possible experiment. There is no ocean large enough, and a giant gaseous planet would not remain intact in such a situation. Saturn's atmosphere consists mostly of hydrogen and helium. Its upper clouds are muted gold, cream, and gray, with bands less visually contrasted than Jupiter's. Deep storms occasionally rise into brighter visibility. The planet rotates in about 10.5 hours, though measuring the rotation of its interior is difficult because there is no solid surface and the magnetic field is unusually symmetric. Saturn also emits more energy than it receives from the sun's slow contraction contributes, and helium may separate from hydrogen at depth, falling inward and releasing gravitational energy in a process sometimes described as helium rain. Its magnetic field forms a broad magnetosphere populated by particles from the solar wind, rings, and moons. Enceladus supplies water-rich material that becomes ionized and spreads through the system. The rings extend across hundreds of thousands of kilometers while remaining astonishingly thin. Most ring particles are water ice. They range from dust grains to boulders and perhaps larger temporary clumps. The rings are divided into broad bands and narrow gaps. The A, B, and C rings dominate the visible system. The Cassini division is not empty. It contains much less material than the neighboring rings. Fainter rings extend inward and outward. The structure is maintained by gravity. Moons open gaps, confine edges, launch waves, and exchange angular momentum with particles. Resonances create repeating patterns. Small embedded moonlets produce propeller-shaped disturbances. The rings behave like a natural laboratory for disk physics. Similar processes operate in protoplanetary disks and galaxies, though at very different scales. The age of Saturn's rings is still debated. Cassini measurements of ring mass and contamination support the idea that the bright main rings may be much younger than Saturn, perhaps hundreds of millions of years old. Other studies show that processes involving pollution, recycling, and particle evolution could complicate simple age estimates. It is safer to say that evidence favors relatively young bright rings while their origin and precise age remain unsettled. They may have formed when an icy moon was disrupted by tides or collision. They may have evolved from older material through repeated destruction and renewal. Different rings may not share identical histories. The rings are changing now. Material falls into Saturn as ring rain. Micrometeoroids darken particles. Moons exchange angular momentum with the disk. Over long periods, the spectacular system may fade or transform. Saturn has 274 confirmed moons as of the current count, far more than any other planet. Most are tiny irregular objects discovered through sensitive surveys. Their orbits form families that probably arose when captured bodies collided and broke apart. The major moons are worlds in their own right. Titan is larger than Mercury and wrapped in a dense nitrogen atmosphere. Methane clouds, rain, rivers, lakes, and seas shape its surface. Organic chemistry produces a global haze and deposits carbon-rich material across dunes and plains. Beneath the crust, Titan may contain deep water-rich layers or a more complex mixture of warm ice, slush, and isolated liquid reservoirs. The traditional model of one global ocean has become less certain as Cassini data are reinterpreted. NASA's Dragonfly rotorcraft is being built to explore Titan's equatorial dunes and impact processed material. Its launch is planned no earlier than July 2028, with arrival in late 2034. Enceladus is much smaller and much brighter. Near its south pole, long fractures called tiger stripes release jets of water vapor, ice grains, salts, organics, silica, and other material into space. The plumes feed Saturn's E-ring. Cassini flew through them, sampling an ocean without landing or drilling. Measurements indicate a global subsurface ocean beneath the ice and interactions between water and a rocky seafloor. Molecular hydrogen and silica particles point toward hydrothermal processes. Enceladus therefore contains water, chemical energy, and complex chemistry. No life has been detected, but the Moon is one of the most compelling targets for future astrobiology missions. Mimas looks like a heavily cratered inactive moon. Its enormous Herschel crater gives it a familiar fictional appearance. Yet measurements of its libration and orbit have led to evidence that a young internal ocean may exist beneath a thick shell. If confirmed, Mimas would show that an apparently ancient, quiet surface can conceal a recently formed ocean. Tethys contains the immense Ithaca Chasma and the Odysseus Impact Basin. Dione has bright ice cliffs created by tectonic fractures. Rhea is heavily cratered and may possess a tenuous oxygen-carbon dioxide exosphere. Iapetus has one bright hemisphere and one dark hemisphere, with an equatorial ridge that makes the Moon's shape especially strange. Phoebe orbits far away in a retrograde path and is probably a captured object from the outer solar system. Material from Phoebe forms an enormous diffuse ring invisible to ordinary eyes. Hyperion tumbles chaotically. Pan and Atlas are shaped by ring material into forms compared with saucers or ravioli. Prometheus and Pandora interact with the narrow F ring. The Saturn system contains almost every category of planetary process: atmosphere, ocean, plume, tectonics, rings, capture, resonance, impact, and chemical cycling. Cassini arrived in 2004 and remained for 13 years. It watched seasons change, flew through Enceladus's plume, mapped Titan with radar, measured the rings, and observed storms and auroras. The Huygens probe descended to Titan in 2005 and transmitted from the surface. In 2017, Cassini ended with a controlled plunge into Saturn. The decision protected Enceladus and Titan from the remote possibility of accidental contamination after the spacecraft could no longer be controlled. During its final grand finale orbits, Cassini passed between the planet and the inner rings, measuring gravity, magnetic fields, atmosphere, and ring mass. The mission is over, but discoveries continue because the dataset is vast. From Saturn, the Sun appears about 1/10 as wide as from Earth and delivers roughly 1% as much energy. The rings would dominate the sky from some moons and vanish edge on from others. Eclipses and shadows sweep across the system. Tiny moons disturb particles. Ice grains move through magnetic fields. We leave the two gas giants behind. Ahead are Uranus and Neptune, grouped together as ice giants but different enough that neither can be understood as a simple copy of the other. Uranus is the seventh planet from the Sun. Its average distance is about 19 astronomical units, nearly 3 billion kilometers. Sunlight requires roughly 2 hours and 40 minutes to reach it. A Uranian year lasts 84 Earth years. The planet's most famous feature is its tilt. Its rotation axis lies almost within the plane of its orbit, giving an obliquity near 98 degrees. Uranus appears to roll around the Sun on its side. Because the rotation is also retrograde under the usual convention, describing north, south, sunrise, and seasonal motion becomes less intuitive than on other planets. Each pole can face decades of sunlight followed by decades of darkness. Near equinox, sunlight reaches the equatorial regions more evenly and day-night cycles occur across much of the planet. The atmosphere does not respond simply or instantly. Heat is stored and transported. Winds move energy. Clouds form at different pressures. Seasonal changes can lag behind the geometry of sunlight. Voyager 2 encountered Uranus in January 1986, near southern summer solstice. The visible atmosphere appeared pale blue-green and relatively smooth. The flyby photographs gave Uranus a reputation as the quietest giant planet. Later telescopes revealed more activity: bright methane ice clouds, storms, dark spots, and changing polar structures appear as seasons advance. The planet was not featureless. Voyager saw it under a particular season, illumination, and viewing geometry. Methane absorbs red wavelengths and contributes to the blue-green color. The atmosphere is mostly hydrogen and helium, with smaller amounts of methane and trace compounds. Beneath the visible clouds, pressure rises into a deep interior unlike either a rocky planet or a simple ball of gas. Uranus and Neptune are called ice giants. The name refers to their likely enrichment in substances such as water, ammonia, and methane compared with Jupiter and Saturn. In the planets today, these materials are not necessarily frozen. They may form hot, dense fluids, ionic mixtures, superionic phases, or other states under extreme pressure. The internal structure is uncertain. Models often include a rocky core, a broad mantle rich in heavier volatile compounds, and an outer hydrogen-helium envelope. The boundaries may be gradual and composition may be mixed. Experiments and simulations suggest that carbon under ice giant conditions could separate and sink as diamond-like material, releasing energy. This remains an inferred high-pressure process, not something directly observed inside Uranus. Uranus emits relatively little excess heat compared with Neptune. Voyager measurements once suggested almost no measurable internal heat beyond absorbed sunlight. More recent analyses and models continue refining that result, but Uranus still appears unusual among giant planets. Why is it so faint internally? A giant impact may have altered the interior and trapped heat beneath stable layers. Composition gradients may suppress convection. The planet may cool through mechanisms not captured by simple models. The extreme tilt may be connected to the thermal mystery, but no final explanation exists. Uranus has a magnetic field that is both tilted and offset. The magnetic axis is inclined by about 60 degrees from the rotation axis, and the field does not pass through the center in a simple dipole pattern. As the planet rotates, its magnetosphere sweeps through space in a complicated motion. Neptune has a similarly unusual field, suggesting that ice giant dynamos may operate in relatively shallow conducting layers rather than deep central metallic cores. Uranus is surrounded by 13 known rings. They are narrow, dark, and much less massive than Saturn's main rings. The Epsilon ring is the brightest. Small shepherd moons help confine some ring edges. The rings were discovered in 1977 when Uranus passed in front of a star and repeatedly dimmed before and after the planet itself blocked the light. Voyager later imaged them, and infrared observations have revealed additional dusty structures. The planet has 29 known moons. The newest was detected in Webb observations made in 2025 and is provisionally designated S/2025U1. It is only about 10 kilometers wide if its surface reflects light like the other small inner moons. The major moons are Miranda, Ariel, Umbriel, Titania, and Oberon. Their names come largely from the works of Shakespeare and Alexander Pope, rather than the classical mythology used for most planetary systems. Miranda has one of the strangest surfaces known. Enormous fault canyons, ridges, grooved terrain, and patchwork regions called coronae suggest intense tectonic activity in the past. The moon may have been heated by orbital resonances, causing internal movement and resurfacing. The old idea that Miranda was shattered and reassembled is not required by modern evidence, though giant impacts may still have influenced it. Ariel appears to have broad valleys and relatively young plains. Umbriel is darker and more heavily cratered. Titania and Oberon are the largest, with fault systems suggesting their interiors expanded as they cooled or froze. Several Uranian moons may contain or once have contained subsurface oceans. Voyager's brief flyby cannot settle the question. Their internal structures, magnetic responses, surface chemistry, and possible activity remain largely unknown. Uranus is the least explored giant planet along with Neptune. Only Voyager 2 has visited. Its closest observations lasted hours, not years. Much of the northern hemisphere was hidden in darkness, and instruments designed in the 1970s had limited sensitivity compared with modern systems. A Uranus orbiter and probe was identified as the highest priority new flagship mission in the latest United States Planetary Science Decadal Survey. That recommendation does not mean a completed spacecraft is already on its way. Mission design, funding, launch opportunity, travel time, and international participation remain matters of planning. A future orbiter could study the planet for years. An atmospheric probe could descend beneath the clouds and measure noble gases, isotopes, winds, and composition. Repeated moon flybys could search for oceans and map geology. Ring observations could reveal particle properties and dynamics. The long journey makes timing important. Gravity assists can shorten travel but depend on planetary alignment. A mission launched in one decade may not arrive until the next. At Uranus, the Sun looks like an extremely bright star rather than a broad disk dominating the sky. Its light is about 1/400th as intense as at Earth, yet still far brighter than full moonlight. We continue outward another 1.5 billion kilometers. Neptune occupies the 8th planetary orbit, about 30 astronomical units from the Sun. Its year lasts nearly 165 Earth years. Since discovery in 1846, Neptune completed its first full orbit only in 2011. It is the only planet whose existence was predicted mathematically before it was deliberately identified through a telescope. Small discrepancies in Uranus's observed motion suggested another body's gravity. Urbain Le Verrier and John Couch Adams independently calculated possible positions. Johann Galle and Heinrich d'Arrest found Neptune near Le Verrier's predicted location. The story is often told as perfect prediction, but the historical details were more complicated. The data contained uncertainties, competing calculations existed, and later understanding showed that long-term agreement was partly fortunate. Even so, the discovery remains a landmark in celestial mechanics. Galileo had recorded Neptune earlier in 1612 and 1613, but treated it as a fixed star. The planet moved too little during his observations to reveal itself clearly. Neptune is slightly smaller in diameter than Uranus and more massive. It is the densest giant planet. Like Uranus, it has a hydrogen-helium atmosphere enriched with methane and a deep interior rich in heavier materials. For many years, familiar images made Neptune appear a much deeper blue than Uranus. Reprocessed Voyager data show that the two planets are closer in natural color than popular images suggested. Neptune remains somewhat bluer, but contrast enhancement had exaggerated the difference to reveal clouds and storms. Neptune is dynamic. Winds reach more than 2,000 kilometers per hour, the fastest measured on any planet. Dark vortices appear and vanish. Bright methane ice clouds form around storms. The Great Dark Spot observed by Voyager 2 disappeared before Hubble later examined the planet, while new dark spots emerged elsewhere. Unlike Jupiter's long-lived Great Red Spot, Neptunian vortices can evolve over years. The source of the energy is partly internal. Neptune radiates substantially more energy than it receives from the sun's slow contraction. Composition changes and heat retained from formation contribute. The contrast with Uranus is one of planetary science's major comparative problems. Two planets similar in size and broad composition behave differently in heat flow, appearance, and perhaps internal layering. Neptune's magnetic field is tilted and offset like Uranus's. Its magnetosphere interacts with the solar wind and sweeps around as the planet rotates. Auroras occur, but the unusual geometry places them far from the rotational poles. Neptune has faint rings. At least 5 main rings surround the planet, along with concentrated arcs within the atom's ring. The arcs persist even though ordinary orbital motion might be expected to spread the material. Gravitational effects from the moon Galatea and interactions among particles help maintain them. The planet has 16 known moons. Triton contains almost all the mass of the satellite system. It moves in a retrograde orbit opposite Neptune's rotation, providing strong evidence that it was captured from the trans-Neptunian region. Capturing such a large object requires energy loss. Triton may once have been part of a binary system. During a close encounter, Neptune could have ejected the companion and retained Triton. Other capture scenarios exist, but all imply major disruption of Neptune's original moons. Triton's orbit later became more circular through tides. The dissipated energy may have melted much of the interior and resurfaced the moon. Its modern surface is young, sparsely cratered, and geologically complex. Voyager 2 saw nitrogen geyser-like plumes rising several kilometers and drifting downwind. Sunlight warmed translucent nitrogen ice, creating pressure below until gas and dark particles escaped through vents. The eruptions demonstrated active seasonal processes at temperatures near -235 degrees Celsius. Triton has a thin nitrogen atmosphere with methane. Its surface includes frozen nitrogen, methane, carbon monoxide, water ice, smooth plains, ridges, pits, and the unusual cantaloupe terrain. A subsurface ocean may exist if enough internal heat and antifreeze compounds remain, though this has not been confirmed. Triton is slowly spiraling inward because of its retrograde orbit. In tens or hundreds of millions of years, it may approach Neptune's Roche limit and break apart, perhaps creating a ring system more massive than Neptune's present rings. The smaller moons include Nereid, whose highly eccentric orbit may preserve the disturbance caused by Triton's capture. Inner moons such as Naiad, Thalassa, Despina, Galatea, and Proteus occupy compact orbits near the rings. Voyager 2 flew past Neptune and Triton in August 1989. It remains the only spacecraft to visit either Uranus or Neptune. The trajectory used Triton's gravity to bend Voyager away from the planetary plane, ending the grand tour of giant planets and sending the spacecraft toward interstellar space. No approved Neptune orbiter is currently on the way. Mission concepts have proposed orbiters, atmospheric probes, and Triton flybys or landers. The travel time and competition for resources make exploration difficult. Ground-based observatories, Hubble, and Webb continue monitoring weather, chemistry, rings, and moons from afar. Neptune marks the end of the 8 planets, but not the end of planetary diversity. Beyond its orbit begins a broad population of icy bodies whose discovery changed the definition of a planet and revealed that Pluto was not alone. The Kuiper Belt is not a narrow ring. It is a thick, donut-shaped region beginning near Neptune's orbit and extending through the outer solar system. The classical belt occupies much of the space from about 30 to 50 astronomical units, while resonant, scattered, and detached populations reach much farther. Hundreds of thousands of objects larger than 100 kilometers may exist there, along with far more smaller bodies. Their total mass is only a fraction of Earth's, far less than models suggest the original disk contained. Neptune's migration scattered much of the material. Some objects were ejected, some moved inward, some entered resonances. Some were thrown into the scattered disk or toward the Oort Cloud. The surviving orbits form a record of giant planet movement. Classical Kuiper Belt objects follow relatively stable paths beyond Neptune. A dynamically cold population has lower inclinations and includes many binaries, while a hot population has more tilted and eccentric orbits. The words cold and hot describe orbital motion, not temperature. Resonant objects complete orbits in simple ratios with Neptune. Pluto is the most famous Plutino, completing 2 orbits for every 3 of Neptune. The resonance prevents close encounters, even though Pluto's orbit crosses inside Neptune's average distance. Scattered disk objects have elongated, inclined paths shaped by past or continuing encounters with Neptune. Detached objects have perihelia too distant for strong present interaction with Neptune, raising questions about how their orbits were produced. Possible causes include early stellar encounters, migration, unseen planets, and the birth cluster of the Sun. Pluto was discovered in 1930 by Clyde Tombaugh. For 76 years, it was commonly listed as the 9th planet. The discovery of many trans-Neptunian objects, especially Eris, forced astronomers to confront whether Pluto belonged to a unique category or a larger population. In 2006, the International Astronomical Union defined a planet as a body orbiting the Sun, massive enough to become nearly round, and able to clear its orbital neighborhood. Pluto met the first 2 conditions, but not the third, and was classified as a dwarf planet. The definition remains debated. Some planetary scientists favor geophysical definitions based on intrinsic properties rather than orbital context. Under those approaches, Pluto and many moons could be called planets. The argument is partly about language and partly about how categories organize nature. Pluto itself is unaffected by the label. New Horizons flew past in July 2015 and revealed a complex active world. The bright heart-shaped region includes Sputnik Planitia, a vast basin filled with nitrogen ice. The ice convects slowly, renewing polygonal cells and erasing craters. Glaciers of nitrogen flow around mountains made from water ice, which is rigid as rock at Pluto's temperature. The atmosphere consists mainly of nitrogen with methane and carbon monoxide. It expands when Pluto approaches the Sun and may partly condense as the world moves outward, though complete atmospheric collapse is not certain. Blue haze layers rise high above the surface. Complex hydrocarbons form through sunlight and settle as reddish tholins. Mountains including Wright Mons and Picard Mons have been interpreted as possible cryovolcanic structures built by eruptions of water-rich material. Their origin remains under study. Pluto may contain a subsurface ocean beneath its ice shell. The absence of obvious global compression features and the history of Sputnik Planitia support models in which liquid persisted, perhaps aided by ammonia or salts. Charon is Pluto's largest moon and about half its diameter. The pair orbit a barycenter located outside Pluto, making their dance unusually balanced. Both are tidally locked, always showing the same face to one another. Charon has a dark reddish polar region, enormous canyons, smooth plains, and evidence of past internal evolution. Pluto's four smaller moons, Styx, Nix, Kerberos, and Hydra, rotate in complicated ways within the binary gravitational field. Beyond Pluto are other dwarf planets and candidates. Eris is slightly smaller in diameter than Pluto, but more massive and follows a much more distant eccentric orbit. Its discovery played a central role in the classification debate. Haumea rotates so rapidly that it is elongated and has a ring. Its moons and a family of related icy objects probably trace a giant collision. Makemake is bright, methane-rich, and accompanied by a small moon. Gonggong, Quaoar, Sedna, Orcus, Salacia, and many others broaden the population. Quaoar has a ring unexpectedly located outside the classical Roche limit, challenging simple assumptions about where ring particles should gather into moons. Sedna follows an extreme orbit with a perihelion far beyond Neptune. Its path may preserve a close stellar passage during the Sun's birth cluster or the influence of distant unseen mass. Claims for a large planet 9 arise partly from apparent clustering among the orbits of some distant objects. Models show that an unseen planet several times Earth's mass could organize such paths. Other studies argue that observational bias, small samples, or alternative early histories may explain the pattern. No Planet 9 has been detected. The hypothesis is a search program, not an established addition to the solar system. New Horizons continued beyond Pluto and flew past Arrokoth on January 1, 2019. Arrokoth is a contact binary formed from two flattened lobes joined gently together. Its shape suggests that small planetesimals could assemble through low-speed collapse rather than repeated violent impacts. The surface is red and only lightly processed. Arrokoth is the most distant and one of the most primitive objects explored closely by a spacecraft. New Horizons is still operating far beyond Pluto. In June 2026, it awoke from its longest hibernation in good health, more than 9 billion kilometers from Earth. It continues studying dust, charged particles, hydrogen in the outer heliosphere, and distant Kuiper Belt objects. Its radio signal takes nearly 9 hours to reach Earth one way. The Kuiper Belt may extend farther in dust and small bodies than older models predicted. New Horizons measurements have detected unexpected dust levels in the outer region, though the cause remains under investigation. We now pass beyond the main belt of icy worlds. The Sun is still the dominant gravitational center, but its light is weak and its solar wind is approaching a boundary. Before reaching the heliopause, it is worth pausing with the objects that travel between the major regions. Centaurs orbit mainly between Jupiter and Neptune. They are small icy bodies whose paths cross or approach those of the giant planets. Their orbits are unstable over long periods. Repeated encounters can send them inward, outward, or out of the solar system. Some centaurs become comets. Others may have arrived recently from the Kuiper Belt. They are transitional objects, carrying outer system ice into the realm of the giants. Chiron, the first object recognized as a centaur, displays comet-like activity even while far from the Sun. Chariklo has a ring system. Other centaurs show jets, color changes, and possible rings or dust structures. Their surfaces have been altered by radiation, impacts, and episodes of heating. Comets are not defined only by where they formed. They become visibly cometary when heat from the Sun causes volatile material to escape. Gas drags dust from the nucleus, creating a coma. Solar radiation and the solar wind then shape tails. The dust tail tends to curve along the orbit. The ion tail points more directly away from the Sun because charged molecules respond to the solar wind and magnetic field. A comet can therefore move partly toward its own tail or appear to have multiple tails. The solid nucleus is usually dark. Its surface contains dust, complex organics, and ice. When activity begins, bright gas and dust can make a small nucleus visible across millions of kilometers. Jets emerge from cliffs, pits, fractures, and sunlit regions. The European Rosetta mission orbited Comet 67P Churyumov-Gerasimenko and followed it through perihelion. The Philae lander reached the surface after bouncing and came to rest in shadow. Rosetta found a world with two lobes, collapsing cliffs, dusty plains, pits, organic compounds, and changing activity. Its measurements showed that cometary water is not all isotopically identical to Earth's oceans. Some comets could have contributed water to Earth, but asteroids and material incorporated during formation were also important. Short-period comets often originate in the Kuiper Belt or scattered disk and are redirected by the giant planets. Long-period comets generally arrive from the Oort Cloud. Their orbits can take thousands, millions, or more years. A new comet entering the planetary region may brighten spectacularly or remain faint. It may fragment before perihelion. It may pass through once and escape. The word periodic can be misleading on human timescales. Halley's Comet returns roughly every 76 years and has been recorded across many generations. Other periodic comets return every few years. Long-period comets may not have visited since before humans existed. The Sun continually alters them. Each close approach removes volatile material. Dust accumulates as a crust. Rotational forces and jets can break the nucleus. Some objects become dormant and resemble asteroids. The boundary between asteroid and comet is therefore not absolute. Rocky bodies can release dust. Icy objects can become inactive. Some near-Earth objects may be extinct comet nuclei. Dust produced by asteroids and comets spreads through the inner solar system. From a dark location on Earth, sunlight scattered by interplanetary dust can appear as the zodiacal light, a faint triangular glow extending along the plane of the planets before dawn or after dusk. The solar system contains dust bands, trails, resonant structures, and particles spiraling slowly inward under sunlight. Micrometeoroids strike planets, moons, rings, and spacecraft. They darken Saturn's ice, release material from Mercury, create lunar flashes, and add particles to atmospheres. Even empty space contains a slow rain of fragments. The farther we travel, the more the Sun changes from a disk into a point. At 100 astronomical units, sunlight is only 1/10,000th as intense as at Earth. Solar panels become increasingly impractical, and spacecraft rely on nuclear power sources. The solar wind continues outward, but it does not expand into perfect vacuum. The Sun moves through the local interstellar medium, a thin mixture of gas, dust, cosmic rays, and magnetic fields within the Milky Way. The interaction creates the heliosphere. A simple illustration often shows a comet-shaped bubble with a rounded nose and long tail. The real structure is more complex and changes with solar activity, interstellar conditions, magnetic fields, and particle populations. The solar wind travels supersonically near the planets. At the termination shock, it slows abruptly below the local speed of sound in the plasma. Beyond lies the heliosheath, a turbulent region of compressed solar wind. Farther out, the heliopause marks the boundary where outward solar plasma is balanced by pressure from the interstellar medium. The heliopause is not a wall. Particles, magnetic fields, and energetic neutral atoms interact across it. Some galactic cosmic rays enter the heliosphere. Some solar particles escape. The boundary shifts and ripples. Voyager 1 crossed the heliopause in 2012. Voyager 2 crossed in 2018 at a different distance and direction. Their measurements showed that the two crossings were not identical. Both spacecraft are now operating in interstellar space in the specific sense that they are outside the heliosphere. They remain gravitationally bound to the Sun only temporarily in trajectory terms because they are moving fast enough to escape. They also remain deep within the much larger region occupied by possible Oort Cloud objects. The Voyagers were launched in 1977. A rare alignment allowed them to use gravity assist from the giant planets. Voyager 1 visited Jupiter and Saturn, then followed a path out of the planetary plane after its close Titan encounter. Voyager 2 visited Jupiter, Saturn, Uranus, and Neptune, completing the only close reconnaissance of both ice giants. Their original planetary missions lasted years. Their interstellar missions have lasted decades. Power comes from radioisotope thermoelectric generators. Plutonium decay releases heat, which is converted into electricity. The available power declines each year. Engineers conserve energy by turning off heaters, subsystems, and scientific instruments. Voyager 1 now operates only a small number of instruments. In April 2026, its low-energy charged particle instrument was shut down to preserve power. Voyager 2 also has only selected instruments remaining. The surviving magnetometers and plasma wave instruments continue measuring a region no other spacecraft has reached. Signals are extraordinarily weak. Voyager 1's one-way signal time is already about 23 hours and continues to grow. A command requires almost a day to arrive and almost another day for confirmation to return. The spacecraft transmit with power comparable to a small light bulb. By the time the signal reaches Earth, it is unimaginably faint. Large antennas of the deep space network collect it from the background noise. The Voyagers carry golden records. Each record contains sounds, music, greetings, images encoded in analog form, and information intended to represent Earth. They were not launched because anyone expected them to be found. The records were gestures toward deep time. In tens of thousands of years, the spacecraft will pass within a few light years of other stars. They will not arrive as functioning messengers. Their power will be gone and their transmitters silent. They will continue as inert objects unless collisions or gravitational encounters alter them. The heliopause is one possible edge of the solar system. It is the edge of the Sun's dominant particle wind, not the edge of its gravity. The planets in Kuiper Belt lie mostly within the heliosphere. Parts of the scattered disk extend beyond it. The Oort Cloud, if it has the expected scale, lies almost entirely in interstellar space. This means much of the solar system exists outside the solar atmosphere. An object can orbit the Sun while moving through the galaxy's interstellar environment. Beyond the heliopause, galactic cosmic rays become more intense. These high-energy particles originate from sources such as supernova remnants and perhaps other energetic events. The heliosphere reduces their intensity within the planetary system but does not eliminate them. The size of the heliosphere changes as the Sun moves through different interstellar clouds. In a denser region, external pressure could compress the bubble. In a more rarefied region, it could expand. Over geological time, Earth's cosmic ray environment may have varied partly because of the solar system's galactic journey. Evidence for direct effects on climate or biology is complex and should not be overstated. The Sun itself orbits the center of the Milky Way in roughly 230 million years. Since formation, the solar system has completed about 20 galactic orbits. It has passed through changing stellar neighborhoods and may have migrated from its birth radius. The original sibling stars born from the same cloud have dispersed through the galaxy. Astronomers search for solar siblings using chemistry and motion, but no definitive list exists. After billions of years, the signals are difficult to reconstruct. The outermost comets preserve some memory of the Sun's early stellar environment. The Oort Cloud has never been seen directly. No telescope has resolved its population as a cloud. Its existence is inferred mainly from long-period comets arriving from many directions on nearly parabolic orbits. Jan Oort developed the idea in 1950, building on earlier work about cometary reservoirs. The cloud is expected to be roughly spherical in its outer region rather than disc-shaped like the planets and Kuiper Belt. Its inner boundary may begin around 2,000 to 5,000 astronomical units. The outer boundary may extend from 10,000 to 100,000 astronomical units, perhaps as far as 1.6 light-years. These estimates are broad because the population is unseen and because the boundary depends on orbital stability. The Oort Cloud may contain hundreds of billions or trillions of icy bodies. Its total mass is highly uncertain. Most objects would be small, dark, and separated by enormous distances. Calling it a cloud does not mean comets fill the sky from one another. A traveler within it might pass for years without approaching any nucleus closely. The leading formation model begins near the giant planets. Icy planetesimals formed in the early outer disk. Encounters with Jupiter and Saturn gave some enough speed to escape entirely. Others were thrown into extremely elongated but still bound orbits. At great distances, the tide of the Milky Way and encounters with stars altered the directions of those orbits, producing a broad spherical distribution. The Sun's birth cluster may have helped shape the inner cloud and could have contributed captured material from other stars. The Oort Cloud may therefore contain objects that formed at different solar distances and perhaps a small number that formed outside the solar system. A comet can remain dormant there for billions of years. Then a passing star or galactic tide changes its orbit slightly. The distant object's perihelion falls inward. It begins a journey that may last millions of years before reaching the planetary region. As it approaches the Sun, volatile ice awakens. A body that was invisible throughout human history develops a coma and tail. It becomes a great comet, crosses our sky, and may never return. The planetary system can alter it again. Jupiter may eject it, shorten its orbit, tear it apart, or redirect it. The Sun may destroy it. A planet may capture or collide with it. Long-period comets are messages from the boundary, but their journey changes the message. Surface layers are heated and lost. Rotation changes. Fragments separate. Interpreting the original composition requires accounting for this processing. The outer Oort Cloud overlaps the region where the Sun's hold becomes fragile. At 100,000 astronomical units, the nearest stars exert noticeable influence. Galactic tides continually reshape orbits. A passing star need not come extremely close to disturb distant comets. The Sun's heliosphere, the broad region where its gravity dominates against the galaxy, is not identical to a fixed Oort boundary and depends on direction and motion. The solar system fades into the Milky Way rather than ending at a fence. The nearest star system, Alpha Centauri, is about 4.37 light-years away. If the Oort clouds of the Sun and nearby stars extend far enough, their outer gravitational populations may approach or overlap in a very broad sense, though individual objects remain sparse. Stars occasionally pass much closer than Alpha Centauri is today. The star Gliese 710 is expected to pass within a fraction of a light-year in about 1.3 million years, likely perturbing Oort cloud comets. Predictions improve as stellar positions and velocities are measured, but exact future paths carry uncertainties. A close stellar passage does not automatically produce immediate danger. Comets disturbed at thousands of astronomical units can take a very long time to fall inward. Any increase in comet flux would unfold over extended periods. Objects also enter from outside the solar system. In 2017, astronomers discovered 1I Oumuamua, the first recognized interstellar object passing through the planetary region. Its hyperbolic orbit showed it was not bound to the Sun. Its shape, rotation, color, and small non-gravitational acceleration produced debate. Explanations include outgassing difficult to detect, unusual volatile ice, dust-driven effects, and other natural processes. No evidence requires an artificial origin. In 2019, Comet 2I Borisov became the second confirmed interstellar visitor. It displayed a clear coma and tail and resembled a natural comet, while its chemistry offered a sample from another planetary system. The discovery of two objects within a few years suggests many interstellar bodies pass through, most too faint to notice. More powerful surveys should find them earlier and in greater numbers. In 2025, a third interstellar comet, 3I Atlas, was identified moving through the solar system. Spacecraft and observatories studied it from multiple locations, providing another rare opportunity to examine material formed around another star through remote observations. Each visitor crosses the same regions we have toured, but does not belong to the Sun. Its path is open rather than closed. It enters, curves under solar gravity, and departs. The distinction between solar and interstellar material is therefore not absolute at every moment. The solar system ejects objects. Other systems do the same. The galaxy carries them between stars. Some may eventually be captured under favorable conditions, especially during the crowded birth of stellar systems, though permanent capture by the modern Sun is difficult without a way to lose energy. The edge of the solar system is thus a place of exchange. Solar wind meets interstellar plasma. Cosmic rays enter. Comets wait in weak orbits. Stars disturb them. Interstellar objects pass through. Voyagers carry small records outward. The boundary is not empty, and it is not still. Let us look back from there. The Sun is now only a bright point. The planets are invisible without precise instruments. Their orbits occupy a region so small that they nearly merge into the star's glare. Neptune, which seemed like the edge of the planetary system, lies close to the center on the scale of the Oort Cloud. The heliosphere forms a bubble nested inside a much larger sphere of possible cometary orbits. Beyond both lies the Milky Way. Distance changes the meaning of home. From Earth, the solar system is the sky divided into sun, moon, planets, and wandering lights. From Mars, it is a yellow-white star with Earth as a bright inner planet. From Jupiter, the inner worlds never stray far from the Sun in the sky. From Neptune, sunlight is dim but still defines day. From the Oort Cloud, the Sun is one star among many, distinguished mainly because gravity still binds the observer to it. The solar system is often described as ordinary. The Sun is a common type of star, neither extremely massive nor extremely small. Planetary systems are common. Rocky worlds, giant planets, debris disks, and small bodies occur around other stars. But ordinary does not mean identical. Every system reflects its disk, stellar environment, migration history, collisions, and chance encounters. Some stars host giant planets extremely close to their surfaces. Some contain compact chains of super-Earths. Some have broad debris disks, highly eccentric giants, or planets around two stars. Our system has no planet larger than Earth and smaller than Neptune, even though such worlds are common in the galaxy. Its small rocky planets occupy the inner region, while giants remain farther out. Jupiter's orbit is nearly circular. The major planets share broadly aligned orbital planes. These features may have helped maintain long-term stability, but we do not yet know how typical the full architecture is. The word quiet in this tour does not mean nothing happens. The sun erupts, planets storm, moons flex, comets fall, asteroids collide, rings evolve, atmospheres escape, orbits shift. Quiet means that these changes occur across distances and times that make them appear calm from a human viewpoint. A storm can last centuries. A glacier can flow over millions of years. A moon can spiral inward for tens of millions. A comet can wait billions of years before one bright passage. The system is active without hurry. Its future will be active as well. The sun will brighten. Earth's surface will change. Moons will recede or fall inward. Rings will spread and darken. Comets will be disturbed. Passing stars will alter distant orbits. When the sun becomes a red giant, the architecture of the inner system will be transformed. Mass lost from the sun will weaken its gravitational hold, causing surviving planetary orbits to expand. The white dwarf remnant will illuminate debris, planets, and perhaps comets under a different sky. The outer planets may survive the red giant phase, though their moons, atmospheres, and orbits will respond to changing sunlight and mass loss. Distant Oort cloud bodies will become more weakly bound and more easily stripped by the galaxy. Over still longer periods, encounters among planets and stars introduce uncertainty. The major planets are dynamically stable over billions of years in most simulations, but the inner system contains chaotic sensitivity. Mercury has a small probability of developing a highly eccentric orbit over very long times, potentially leading to collision or ejection. A small probability is not a prediction of what will happen. It reveals that precise orbital forecasting becomes impossible far into the future, even under deterministic gravity, because tiny uncertainties grow. The present solar system feels permanent because human life is brief. Its apparent permanence is a scale effect. The craters on Mercury, the clouds of Venus, Earth's oceans, the valleys of Mars, Jupiter's storms, Saturn's rings, Uranus's seasons, Neptune's winds, Pluto's glaciers, and the distant comets are all temporary configurations. They are long-lived enough to become worlds and short-lived enough to evolve. Now let the view contract again. The Oort cloud fades first because it was never visible. The heliosphere becomes a small magnetic bubble around a star. The Kuiper Belt becomes a thin disk of cold points. Neptune and Uranus move inward on the map. Saturn's rings become unresolved. Jupiter becomes a bright moving dot. The asteroid belt collapses into a subtle band. Mars reddens. Earth turns blue. Venus shines through clouds. Mercury crosses the sun's glare. At the center, the sun again fills the sky. Every region in the tour belongs to one connected history. The iron in Mercury, the carbon dioxide of Venus, Earth's oceans, the dried channels of Mars, the organics in Bennu, Jupiter's hydrogen, Saturn's ice, Uranus's tilt, Neptune's captured Triton, Pluto's nitrogen glacier, and the comets of the Oort cloud all emerged from one forming system. The materials separated, mixed, migrated, collided, froze, melted, escaped, and returned. No planet developed alone. Jupiter altered asteroids. The moon altered Earth's tides. The sun shaped every atmosphere. Neptune organized the Kuiper Belt. Passing stars shaped the outer comet cloud. The Milky Way surrounds everything. And on Earth, one collection of solar system matter learned to build instruments and send them outward. Mariner crossed to Venus and Mercury. Viking landed on Mars. Voyager toured the giants. Galileo entered Jupiter's system. Cassini circled Saturn. New Horizons crossed Pluto's path. Hayabusa 2 and OSIRIS-REx returned pieces of asteroids. Perseverance sealed Martian rocks. Bepi-Colombo approaches Mercury. Europa Clipper and JUICE travel toward Jupiter. Dragonfly is taking shape for Titan. The missions are small compared with the worlds they visit. Their instruments operate for years and return streams of numbers that become maps, images, chemical histories, and new questions. Exploration changes the solar system without moving its planets. Mercury becomes a world with ice. Venus becomes a climate history rather than a bright star. Mars becomes an archive of lakes. Asteroids become wet parent bodies and broken cores. Moons become ocean worlds. Pluto becomes active. The heliopause becomes a measured boundary. Knowledge adds depth to the familiar order. There are still many places no spacecraft has visited closely. No orbiter has studied Uranus or Neptune. No lander has operated on a comet beyond Philae's brief surface mission, and none has entered a Kuiper Belt world. No probe has sampled an ice giant's deep atmosphere. No mission has flown through the Oort Cloud. There are unseen moons, uncounted small bodies, and perhaps large distant worlds still waiting for discovery. The solar system is our nearest cosmic environment and remains incompletely known. That is part of its quiet beauty. It can be familiar enough to name and vast enough to surprise. 8 planets do not finish the map. The edge depends on the question. The story depends on the scale. The sun is a disk in our sky, a star in the galaxy, and the center of every orbit we have followed tonight. Earth is a planet among planets, and the only known place where the tour can be understood. Far beyond Neptune, the voyagers continue through plasma no earlier spacecraft measured directly. Farther still, unseen comets follow slow paths under the combined influence of sun and galaxy. The darkness between them is immense. Yet the darkness is crossed by gravity, particles, magnetic fields, dust, radio signals, and light. The solar system is not a set of isolated objects suspended in emptiness. It is a connected, evolving region inside a larger connected galaxy. For 4.6 billion years, the planets have moved around the sun. For a tiny fraction of that time, human beings have known what those moving lights are. For an even smaller fraction, machines have traveled among them. The tour ends, but the motion does not. Mercury continues through its short year. Venus turns beneath its clouds. Earth carries its oceans through sunlight. Mars gathers dust on the floor of Jezero crater. Asteroids cross ancient resonances. Jupiter's magnetic field sweeps past its moons. Saturn's rings exchange particles and momentum. Uranus advances through a season lasting a human lifetime. Neptune's winds circle a world 4 light hours from the sun. Pluto's nitrogen ice convects beneath a distant sky. New Horizons listens to dust and plasma. Voyager's fading transmitters send their narrow signals home. And in the Oort Cloud, objects no telescope has ever seen complete orbits lasting millions of years. This is our solar system, not a compact diagram, but a depth of darkness shaped around one star. Not a finished museum, but a history still unfolding. Not the whole universe, but the place from which the universe first became visible to us. Good night.